question asks us whether a fluoride radical will be selective at forming one carbon radical over another, starting with propane as our starting material. To do that, we'll use bond dissociation energies to calculate delta H for each of these reactions and see if there's any selectivity difference. Let's start adding some bond dissociation energies. We are breaking a secondary carbon-hydrogen sigma bond in our starting material that has a bond dissociation energy of 95 kilocalories per mole. And we're forming a hydrogen-fluorine sigma bond that has a bond dissociation energy of 136 kilocalories per mole. Our calculation for delta H, the equation for delta H, is the amount of energy we need to input into the system to break the bonds, so 95 kilocalories per mole, minus the energy we get out by forming bonds, 136 kilocalories per mole. When we do this calculation, we see that the delta H for this step in this reaction is negative 41 kilocalories per mole. That is an exothermic process. An extremely exothermic process. This is a very large negative delta H. Let's look at the delta H for the other possibility. Here we're breaking a primary carbon-hydrogen sigma bond. I didn't have room on the screen to put that table, but the bond dissociation energy for a primary carbon-hydrogen sigma bond is 98 kilocalories per mole. We're forming the same hydrogen-fluorine sigma bond, so it has the same bond dissociation energy, 136 kilocalories per mole. We'll use the same delta H equation. Bonds broken minus bonds formed. And this equation tells us that the delta H for this reaction is negative 38 kilocalories per mole. Also extremely exothermic. Because this is exothermic, though, it is not going to be selective for forming one carbon radical over the other. This will not be a selective reaction and is so exothermic, it's releasing so much energy that, honestly, you're probably going to start the lab on fire. Please don't do this. There's a reason we don't use fluorine for radical halogenations. This reaction is not selective and is extremely exothermic.